I'd like to introduce Pierre-Marc Chouadin. He is a co-founder and CRO for Imeka and also a faculty member at the University of Sherbrooke. Today's webinar title is AI, What's Under the Hood? Why and How Does It Work? So Pierre-Marc, I'll let you take over and get started.
Thank you. Very happy to be here and welcome to this presentation on AI, What's Under the Hood. So as you may already know, AI is a very large R&D area, which we may divide very well in three great branches. The so-called unsupervised learning or big data branch, the reinforcement learning branch, which is very useful in robot navigation and game AI, and supervised learning. In this presentation, we'll be focusing more on supervised learning and more specifically on neural networks. Why? Because probably 90% or 95% of the reason why you've been hearing so much about AI in the news in the last 5 or 10 years is because it's exactly of neural networks. In this presentation, I'll try as best I can in 30 minutes to dig under the hood of what a neural network is. What is a neuron? What does it mean to train a system? And why does the system work so well? Is this just a flavor of the day? Or is it something that is there to stay for many years to come? Now, without further ado, let's start with a very simple example that I'm sure all of you will understand. So it's an example where you have patient in the hospital and the patients are coming to the hospital and each time go through a predefined protocol. And this protocol is very simple because this is a simple example. Each patient is got his body temperature measured and cardiac frequency measured. And then the doctor comes with a diagnostic. Is the patient sick or healthy? And we do this for patient 1, patient 2, patient 3, all the way to patient N. And we put all of these information into a table. We'll call that table D. Each time you see the letter D in the presentation, you may have this table in mind. This table has 2 columns. The first column are the observations, which are vectors, 2D vectors. So why 2D? Because each patient is assigned to 2 values, body temperature and cardiac frequency, and we have a target. In this case, it's a binary target. Is the patient sick or healthy? Now, this table can be represented by the following scatter plot. And in this plot, each patient is a point in a 2-dimensional space. The horizontal axis is the body temperature, and the vertical axis, the cardiac frequency. And on one hand side, we have the sick patient, and on the other side, the healthy patient. Now, still in our example, we have a new patient that comes to the hospital, and we would like to know automatically if that person is sick or not. What can we do? Well, we will have this patient go through the same protocol. So that means we will measure his body temperature and cardiac frequency. And so this new patient will become a new point into this 2-dimensional space. And depending on where the point will fall, will determine if the patient is likely to be sick or healthy. Now, how can we do this? How can we determine if a point is on the sick side or the healthy side? Well, there are many ways of doing this, but one very common solution is to separate or divide the feature space into different regions. In our case, the sick and the healthy region. We do this like this. This is the illustration of what I mean by dividing the feature space. So we have a red region for the sick section of the feature space and the green region for the healthy sections of the space. Now, depending on where this new patient falls, is it on the red section or the green section, the patient will be targeted as a sick patient or a healthy patient. Now, this separation is done mathematically. And we'll represent this mathematical function which divides the space by the letter Y. Okay? Now, we had the letter X, which is a point in the 2-dimensional space. So X, in our case, is just 2 values, body temperature and cardiac frequency for a patient. And Y is a function that says, are you on the red side or on the green side? Now, one of the questions is, how do we split the feature space mathematically? So this y is a function there. So what does this function look like? And for the next couple of slides, we'll be looking at some math. These are not very difficult mathematics, but I think we have to go through it in order to better understand how a neural network works. Well, let's go back to the very basics, a definition of a line. So if you remember, go back to your high school years, definition of a line is given by y equal mx plus b, where x is the horizontal axis, y is the vertical axis, and we have this red line. So any point that falls onto the red line should satisfy this equation here. And if you remember well, m is called the slope, and b is called the bias. And again, if you remember well, the slope can be measured by taking the ratio between delta y over delta x. And the bias is the distance to the origin. So if your line goes through the origin, b is equal to 0. Now, here it says m equals to delta y over delta x. So in this equation here, let's replace m by delta y over delta x. I just replace m by its own definition. Now, one thing we can do, this is very basic algebra, we can multiply this function, this equation here, by delta x. If we do this, we end up by having this equation there. And the term here on the left, y delta x, we can take it on the other side in order to have 0 equal to something. Now, this something here, although it might look a little bit nasty, it's just the exact same definition of the line that we had before, y equal mx plus b. Now, that equation of the line will rename some of its variable, because we have those nasty deltas that we might not like. So the first delta y, we'll call it w1. The minus delta x, we'll call it w2, and the remaining w0. So that would be still the equation of a line. I just renamed some variables and did some rearrangements of the term, but this is still the equation of a line. Another renaming that we're going to do is, instead of having x and y, the two axes, we'll have x1 and x2, which is more convenient because in our simple example, we had, body temperature and cardiac frequency, but we could have had more measurements. And more measurements may eventually leads to hundreds of different measurements, or even thousands of different measurements. So it's more convenient to talk about x1, x2, x3, x4, to talk about the first, second, third, fourth measurement that we made for each and every patient. So the equation of our line is this one here, w1 times x1 plus w2 times x2 plus w0. This equation, although not very complicated, is at the very basis of deep neural networks. So let's take some actual values just to validate our understanding of what a line is. So let's consider this two-dimensional space where x1 and x2 are the two axes, and this red line here. And this red line is defined by the parameters w1 equals 1, w2 equals -2, and w0 equals 4. So these parameters define this line here. So if you take a point that falls exactly on this line, whose coordinates is 2 and 3, well, if you plug those coordinates inside this function there, you will end up with a function that returns 0, which makes sense. The equation of a line says that any point that falls on the line should be equal to 0 according to this equation there. Now, things become much more interesting when we take points that are not on the line. Let's say, for example, this point here that falls on top of the line, coordinate 1 and 6. So if we plug 1 and 6 into this equation, we end up with the value -7, which is a negative value. Even more interesting is if you take a point on the other side of the line, for example, this one at coordinate 4, 1, and you plug the coordinates into the equation, you will end up to have a value of 6, which is positive. That's very interesting. This means that this very simple equation of a line separates the space in two different regions. regions for which points correspond to a negative value, and the regions for the points that correspond to a positive value. And of course, all of the point that falls on the line that equals to 0. Well, that function y here has a name. We call this a classification function. Now, this classification function is the definition of a line that we can also represent by another mathematical operation. We're going to slow down here a little bit. That is called the dot product. Well, the dot product is what? It's the product between two vectors. The first vector contains the weights of our equation, W0, W1, W2, and the second vector contains the parameters. So body temperature, cardiac frequency, and one is for the bias. And the dot product is W0 times 1 plus W1 times X1 plus W2 times X2. This is one of the most simple mathematical operation there is. And we can, for short, represent it by this function, the W times X. Now, a linear classification is a dot product. And a dot product is a very effective operation that is done very quickly on specialized hardware. So that's nice. Now, a very important buzzword, and that is misunderstood by many people, is the notion of training and learning. Well, training and learning is not that complicated. So let's go back to what we had. We had a dataset D. Remember this first dataset that I showed you. The goal of a machine learning algorithm is to find the right parameters, W0, W1, W2, so the parameters of our line, such that the two classes are well separated. So that means the sick patient falls onto the positive side and the healthy patient on the negative side. Now let's consider this illustration furthermore. We have two sets of points, the green points and the red points, which are not very well separated because half of the points are ill-classified because the coordinate of this line is inappropriate. Well, a machine learning or a training algorithm has to, what it does, it iteratively improves the coordinate of the line little by little so that points get well separated. This is what we mean by we show the system positive and negative example, and the system improves. This is nothing more than this. And this is what 99.9% of neural networks do. Now, so far, what do we have? We have a training data set D. We have a classification function. In our case, so far, it's a line. And we have a training algorithm, which finds the parameters W0, W1, and W2 of the system so that the data is well classified. Now, are linear classifiers new? Well, obviously not. You have to go back to the 1950s to see the very first systems. And the very first system is called the perceptron. And the perceptron is still being taught in university classes. So what is the perceptron? The perceptron is nothing more than what we have seen so far. It's the definition of a line. And the line, as I mentioned, it's mathematically a dot product. One thing is that the perceptron implements a graphical model, as you can see here. Well, this graphical model, I'll walk you through it, but it implements exactly that function here, which is the definition of a line. So in this graphical model on the left, we have three circles corresponding to the input variable of the system. Then we have three arrows. Each arrow or connections is associated to a parameter W. And then we have this circle here, which embodies a dot product. In other words, this circle here contains W0 times 1 plus W1 times X1 plus W2 times X2. So the output here is the output of our line definition. The only little difference is that the perceptron doesn't return a positive or negative value. It returns exactly +1 or -1. In a way, you can see this as a system that says you're healthy or you're sick, but nothing more than this. So in order to have +1 or -1, the perceptron adds what we call an activation function, which is a sign function, which returns +1 or -1, depending on, if you're on the positive side or the negative side. Well, look at this. If you combine the dot product with this nonlinear activation function, this gives rise to a very important buzzword, probably the most important buzzword, the neuron. A neuron is nothing more than a dot product and an activation function. And so an artificial neuron has very little to do with a biological neuron, such as those we have in our head. So when we hear sometimes in the news that deep neural nets have an objective of replicating how our brain works, well, this is a little bit an overstatement, shall we say. Now, of course, linear classifiers have very important limits because in reality, points are most of the time not linearly separable. This is the very basics of machine learning. Most of the time when you look at your point, it's just impossible to separate it with a linear classifier. Now, if you go in the literature, you'll find three broad classes of solutions to that problem. First, you may want to acquire more data. Second, use a nonlinear classifier. And third, transform the data. So let's look at the first one, acquire more data. So what do I mean by that? If we go back to our initial example, where each patient got its body temperature and cardiac frequency measured, then followed by a diagnostic. Maybe cardiac frequency and body temperature is not enough to discriminate between healthy and sick patients. So maybe we need to have more data. For example, maybe we should ask the patient, you suffer from a headache, and give me a value between 0 and 10. 0 means no headache, and 10 means an intolerable headache. So in this case here, we have 3 measurements instead of 2. So that means a patient, instead of being a point in a 2-dimensional space, becomes a point in a 3-dimensional space. And if you're lucky, in that third dimension, in that 3D distribution, you can have a plane that would successfully separate the red dot from the blue dots. The beauty of the thing is that the equation of a line is exactly the same as the equation of a plane, whereas in the plane, there's one extra term, W3 times X3, to account for the third dimension. What does that mean for a perceptron? Remember, this was the perceptron we had in a 2-dimensional space. Now, if we have a 3-dimensional space, well, the perceptron embodies exactly the same operation, which is a dot product followed by an activation function. The only difference is that we have a third bullet here on the left. Of course, you can have as many input variables as you want without changing the very nature of the perceptron. So that's great. So far, what do we have? We have a training data set, which contains a series of observations, not necessarily two. We may have an arbitrary large number of points. We have also linear classification function, which we can represent by a graphical model, such as this one. And we have a training procedure. Now, I said that when we have linearly separable data, we may use a nonlinear classifier. Due to time, we'll skip over this. And then we'll focus on transforming the data. So what do I mean by transforming the data? Let's consider this toy example, this synthetic example, where we have red dots and blue dots that cannot be separated by a linear classifier, at least not without significant errors. Wouldn't it be great if we had a magic wand that would take those points and project it to a new mathematical space, in which space would be very easy to fit a linear classifier to separate the red dots from the blue dots? That would be great. Well, you can take my word for it. This is no magic. In fact, there are functions that are capable of doing this. In fact, when you implement a machine learning algorithm, most of the time you start with a training data set. Then you would transform the data to make sure that they are linearly separable. Then you would use a linear classification function to separate those points. And of course, you will do this throughout the training procedure. Now, what does F looks like? I'll be skipping over many, many details, but down the road, if you use a neural network, if you start by multiplying the number of neurons in your neural network, well, your neural network will both transform and classify the data. It will do both operations at the same time. This is great, and this is probably the reason why neural networks are so popular. This is called end-to-end training. You do both operations in one step. So it's one stone, two birds. Now, how do we get to do this? Well, we need to get deeper in the network. And this will give rise to another very important buzzword, deep learning and deep neural nets. So let's go back to what we had before. Remember, we had points in a two-dimensional space, body temperature, Kazakh frequency, and we said that we could separate those, linearly separate those plots with the perceptron. And the perceptron is illustrated as follows. We have an input layer, we have an activation function, and we have an output neuron, which essentially returns +1 or -1. Now that neuron there output a real value. So it's a value between -infinity and +infinity. It's a real value. Now if, for fun, we decide to have, let's say, for example, 3 neurons instead of 1. Well, each neuron does whatever it has to do. It implements a dot product followed by an activation function. So that means the output of these 3 new neurons is a real value. So the output of this layer are 3 values. It's a vector of 3 values. Now, if, for fun, we decide to take these 3 output and connect it to a new neuron. So that new neuron, and I understand that that may be more or less intuitive, but that new neuron does whatever it has to do. It does a dot product followed by an activation function. That neural network contains an input layer, an output neuron, and in the middle, an hidden layer. Well, when you do something like that, and we haven't done much, it's just a series of dot products and activation function, well, something almost magic happens when we do this. Let's take, for example, this 2D scatter plot where we have red dots and green dots, and we would like to separate. If you use a linear classifier, at best you will have a result like this one. Most of the points are going to be well classified, but the other set of points, maybe half of the points, are going to be ill classified. This is a problem of what we call underfitting. Now, if you just add one hidden layer, you get a result like this one. This almost looks like magic. The system is very simple. It's just a series of dot products and activation function, and all of a sudden, the system seems to act in a nonlinear fashion. Well, let's dig into what's going on here. Let's consider this neural network, which has an input layer of points in a two-dimensional space, an hidden layer of 3 neurons, and an output layer of 1 neuron. Now, as I mentioned before, if we have more than 2 observations, we have k observation, there's no problem. We can multiply the number of input neurons as we wish. In the hidden layer, we can also add as many neurons as we want. Each neuron in the hidden layer does whatever it has to do. It's a dot product followed by an activation function. Now, nothing prevents us from adding extra layer. For example, here I have 2 hidden layers, but I could have more. Like in this case here, I have 4 hidden layers with a series of neurons for each layer. At the end, we have a network that becomes deep. Why deep? Because it has many hidden layers. So a deep neural net is just a neural network that has many layers of neuron connected with each other. Now, a neural network like this one is often called a multilayer perceptron. And the multilayer perceptron takes a vector x as input. All of the hidden layers, this is our magic one. This is the function f that I was mentioning before, the function f that takes a set of points x that are non-linearly separable and project it to a new space. In this example here, it's a space in the 1, 2, 3, 4, 5, 6, 7 dimension that are linearly separable. And at the end, we have a linear classifier. That's a multi-layer perceptron. So here's a very simple one that I implemented not so long ago. So we have a scatter plot of points that are not linearly separable. This is the input of our system. And the output of the system, I've put two neurons here. So if we look at the output of those two neurons, we realize that once the system is correctly trained, the output of those two neurons are points that are linearly separable. That's great. And the output is just a function that separates the blue dots from the red dots. Now, as I mentioned before, if you have more than two classes, well, you can add extra output neurons. So if you have three classes, all you have to have is 3 output neurons. And I'm skipping over a few details, but this is how it is. So if you had 10 classes, you would just have to have 10 output neurons. If you have 1,000 classes, well, you would need to have 1,000 different neurons at your output. Now, so far, we have a training data set D. We need to transform the data and linearly classify the data throughout the training procedure. Well, when you use a deep neural net, you can replace those two operations with just one system. And that system does it all at the same time. It disambiguates the points and classify it at the same time. Now, how do we classify an image with a deep neural net? Because the buzz around deep neural networks is often related to image analysis. Well, let's consider this simple image. This is an image from a very well-known data set called MNIST, which contains 28 columns and 28 rows for a total of 784 pixels. And each of those pixels is associated to a value between 0 and 255. So 0 is black, 255 is white. Now, you can take all of those pixels and consider it as vector, as an element of a vector. So then you would have a vector of 784 dimension. And if your first hidden layer here contains 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different neurons, then between your input and hidden layer, you would get 7,840 different parameters. Now, this example, this image is kind of trivial, I would say. So if you look at a more realistic example, for example, this MRI image of a brain, which contains 256 by 256 pixels, then we would have an input vector of more than 65,000 dimension. And so the number of parameters just in the first layer would be more than 500,000. This is a lot. This is a lot considering that down the road, we would like to have deep neural nets with many layers. Here, we only have one layer, and we already have almost 1 million parameters. Now, if we consider the 3D volume of a brain, which would say contains 256 of those images, then we get a whopping number of 160 million parameters in the first layer. And this is far too large to be handled even with modern-day computers. And this was, for many years, an important limit of neural networks. The only solution to this is to reduce the number of parameters. How can we do this? Well, you will have to take my word for it, because this is really not intuitive. Even my students need a lot of time before they understand it for real. But one thing we could say is that each neuron, instead of connecting it to the output of every neuron in the previous layer, are connected to just the so-called neurons in front of them, like this one here. Each neuron here are connected to the previous 3 neurons in front of it. Furthermore, the weights are being shared across the neurons. So I understand this is not very intuitive, but this gives rise to an operation called convolution. Mathematically, there's no difference between having a neural net with sparse connection, shared weights, and a convolution. It's exactly the same thing. So what does that mean? It means that a neuron in the first layer, instead of being connected to every pixel in the input image, is connected to a subset of pixels in the input image. And the next neuron is connected to another subset of pixels in the image, and so on and so forth. Now, interestingly, if you take the output of all of these neurons, as I mentioned before, the output of those neurons is a real value. So you can take the output of all those neurons and put it in the image to visualize it. Then you'll get a filtered version of your input image, once the system is trained, of course. And that's interesting. If you keep on multiplying the number of neurons and visualize the output of those neurons, you'll see that your first layer ends up as a filtering operation that takes your input image and filter it. That's interesting. And if you start adding more layers, well, those new layers will have neurons that will filter the filtered image of your input image, and so on and so forth down the road. And as we mentioned before, the output of your system is a linear classifier. This is called a convolutional neural networks. And these CNN networks are extremely popular when it's time to process images. You will find it absolutely everywhere. If you have more than two classes, of course, all you have to do is to multiply the number of neurons at the output of your system. What do you have here? It's the same thing as before. You have a system that inputs vector X. In this case, it's an image. And probably the image in that data set are highly convoluted. So that means they're not linearly separable. But all of those conv layers serve as our magic one, our function f, that will project the images to a new dimensional space where every point is linearly separable. And at the end, it's a linear operation that will classify our images. So here's a nice example from the literature, taken from a paper from 2018, where the author wanted to process MR images and to predict if there's a brain tumor or not in that MRI image. What you can see on the left are the MRI images, so the input of our system. Then we have a series of neuron layers that are in fact convolution layers, but it's a series of neurons, and each neuron implement a dot product with an activation function. And at the end, we have a linear classification operation which predicts normal or abnormal. So as I mentioned before, when you process images, you can do classification, for example, cancer nor cancer, but you can do other things, like for example, segmentation. You can segmentation means to classify each and every pixel individually. Or you can do a regression, which is to output a real value, which, for example, would be the volume of that tumor here. Now, here's a couple of examples of neural networks that are being used on an everyday basis at Imeka. The first tool that we use pretty much every day, and now that works 99.999% of the time, is a brain extraction tool. Based on a T1 weighted image, the goal of this CNN, ConvNet, is to classify each tissue as being part of the brain, the red section that you see here, or not part of the brain. Like, for example, the skull, the eye socket, and so on and so forth. That works very well. Another tool that we have is a brain lesion segmentation. So here the goal is to process an MR image of the brain, but now it's a two-class segmentation for each pixel, lesion versus non-lesion. These are lesions of Alzheimer's disease patient, typically white matter hyperintensities. Not so long ago, we started working on multiple sclerosis lesion segmentation. It's pretty much the same idea, but instead of being brains of Alzheimer's disease patient, it's brain of patient suffering from MS. Another example, we have a tool for segmenting T1 images in white matter, gray matter, and CSF. But more recently, we developed another CNN whose goal is to process diffusion-weighted images directly and to classify its pixel in 12 different classes: white matter, CSF, gray matter, as well as different regions like ventricles, hippocampus, putamen, etc. So the beauty of this is that thanks to deep neural nets, in the near future, we'll be able to acquire diffusion images without having to acquire a T1 image, and to process diffusion images directly without the need of a structural image. Another project that we are working on now is using deep learning for quality control. So when you acquire diffusion MRI, sometimes those images might suffer from a couple of limitations, like, for example, slice drop, an excessive amount of noise. Maybe the patient has moved, and so because of that, the subsequent operation that we might do on these images would fail or produce erroneous results. Up until very recently, the detection of size drop, noise, and patient motion was done manually. Now we're currently developing a deep neural net that would classify these images as, containing slice drop, yes or no, containing excessive amount of noise, yes or no, and so on and so forth. Another thing that we have been working on is using deep learning for diffusion MRI tractography. So the idea is to use deep learning to recover fiber tracks in the brain. So fiber tracks in the brain, yes. And so recently we've got results that are very close to state-of-the-art non-deep learning algorithm, and I'm pretty confident that in the near future our machine learning algorithms will outperform non-deep learning algorithms. Another thing that we have been working on, which is very successful, is to do bundling. That means based on the fibers that we have, we can divide those fibers into different bundles or different regions. For example, if you consider on the left these fibers that got recovered, so these are connections in the brain, fibers in the brain, we can classify those fibers into a different number of bundles, like, for example, these bundles of the limbic system on the right. This is extremely effective with a deep neural network. Last example is domain adaptation. Like, if you acquire MRI images from different hospitals, you might end up having these kinds of different signals. And since the signals from one hospital to another one is very different, it's difficult to have a reliable overall study without a bias towards one different type of data versus the other type of data. So in order to compensate for this, we use a CNN to harmonize the data so that all of the data, irregardless from where the hospital they were acquired, all look the same. Now, in conclusion, neural networks are very effective. And why are they very effective? Because they implement a so-called end-to-end training. They disambiguate the data. That means they project data into a space where everything is linearly separable, and they do the classification at the same time. It's very effective, very flexible also. Maybe a little bit too flexible sometimes. But let's say, for example, you need more data, just add some more input neurons. You need more classes, add more output neurons. You need more capacity, add more layers. This is very flexible and very easy to do. If you have too many parameters and you're processing signals like 1D signals, sound, or images, or video, then you can use the convolution trick to reduce drastically the number of connections and the number of parameters that ought to be learned. So this is a third reason. And the fourth reason, which is very important, we now have a lot of annotated data and well-annotated data and lots of processing power. And with more data and more processing power, we can learn deeper networks with more capacity and get some even more impressive results. So on this, I would like to thank you. That's the end of my presentation.
Okay, great. So now we're going to open up the floor to question time. So if anyone would like to ask a question, please unmute your microphone and go ahead. Any questions from anyone? Don't be shy.
Sorry, it was supposed to be a 30-minute presentation. It took 36 minutes, so maybe people left.
Okay, so there's a question on the chat. Yes, you can ask there. So if people want to type the question on the chat, you're free to do that. If you want to unmute the microphone and ask, that's okay too. Everyone understood all the math?
Yes.
I have a question for you. I was, if I'm allowed to, I mean, is it fine? Okay.
Yes, go ahead, Steve.
So yeah, so I think, so as you say, like if you have like non-linear behavior inside your data, I would say like usually you use like hidden layer and stuff like that. That was part of the conclusion. But I was wondering if you are trying to do prediction, not classification. Most of the time, I mean, I'm from ecology, and most of the time when you use like classification and those kind of algorithm, you cannot do prediction because you get surfeiting data. I mean, you surfeit the data. Like if you are trying to go outside of the calibration area that you have, like you cannot do it because most of the prediction has to be inside that calibration area that you use. Does that make sense?
Well, maybe one thing I need to mention is that if I go back to my scatter plots, okay, here. If you train based on a set of data like that, your system is only going to be effective at predicting new sets of data that follows exactly that same distribution. So for example, if this was your training data and your testing data has a set of red points that are shifted to the left or to the right, your system is very well going to fail first. So the distribution of training and test data need to be exactly the same. And this is very difficult when you don't have a lot of data. So if you have millions and millions of examples, then you might start having a good distribution of what your real set of data is. But if you don't have that, then it's true then that your testing data might be different from your training data. And this is where problems start to occur. Now, let me ask you a question. What do you mean by making a prediction? Because when a system classify an image or make a regression, this can be seen as a prediction. So I suspect that you may have a different understanding of this.
Yeah, I wanna. So yeah. So is it? Do you hear me? So
Yes.
I mean, I'm gonna take like one of my. So when you think about climate change, like all the system will behave in new climatic condition. By example, it's an example in ecology. So you don't necessarily have the data to. I mean, you cannot really. That's why we don't like validation and stuff like that, because usually you don't have the data to validate. You know what I mean?
Yes, if you're talking about a system that evolves in time, so that means the kind of data that you have now that is valid as of today might be invalid in the future because things are being evolving, like climate change, as you're saying. Then in this case, unless you have trained your system to be able to adapt to those future changes, your system is certainly not going to work well.
But that's the case. I mean, if you think about like health record and stuff like that, I mean, if you are trying to predict, I don't know, that will not make sense. Like the frequency, the heart frequency rate, like for an individual, but you don't cover all of, I mean, you have to assume that you cover all of the
Yes, yes,
Okay.
you're totally right. This
But
is why I'm saying you need to have, like, let me go back to this example here. That brain extraction tool. Well, that brain extraction tool started to work well when we had more than, I think, 3,000 or 4,000 different images of 3,000 or 4,000 different patients. Before that, the number of patients was not large enough, and so when we would see a new patient, the brain of that new patient would have these slight variation from the other ones we have seen before, and we would have, a couple of pixels that would be ill classified. But as you start to have a sufficiently large data set, and sometimes the data set doesn't need to be that large. If you want to do face recognition and stuff like that, you need a couple of thousand images, but that's not too large before you start getting some very interesting results. But you're totally right. If you're tackling a problem that is evolving in time, like, for example, if you try to predict the stock market. So I don't think that a lot of AI algorithm was able to predict that the stock market would lose almost 50% of its value 2 months ago. Why? Because they haven't seen this in the past. So when you have something that evolves in time, you're totally right. You need to really make sure that your system can take care of this.
thanks a lot. It was a really comprehensive answer.
Okay, Pierre-Marc, we have a question on the chat. I'm happy to read that.
Okay, go.
Hi, great chat, thanks. I'm curious about the harmonizing. Is it better to harmonize images before inferring on them, or just train your model to accept unharmonized input and classify more robustly? In the context of cell nucleus segmentation, for example, it's better to train a model on many different domains and styles of cells to help the model generalize a lot of types.
Yep.
Rather than generate more simplified or ideal input data.
Yeah.
Is it not the same with your different hospital input differences?
Yes. In our case, the thing that might be a little bit different is that the subsequent operations that we apply on the images are not deep learning. They're non-deep learning operations, and they may still be non-deep learning operations for the years to come. And so it's very important for these operations down the road to have really uniform sets of data. So that's why we do this. But if you have a system that can be trained end to end, so let's say, for example, you want to predict brain tumor volumes, for example, and you have data that come from different hospitals, there's no need, or it's hard to tell. We see different types of papers. I think the literature is not mature enough to come with an absolute answer. But one thing is for sure, as soon as you have enough data to train on, and what is enough, it's an open question. But if you have enough data to train on, then you might have a system that is relatively robust to domain adaptation. So my answer is, if you have enough data and that your system is end-to-end trainable, then taking care of domain adaptation might not be super critical. However, in our case, since we use non-deep learning processing, having harmonized images is very critical. I hope it answered the question.
Okay, great. Yes, it answered your question. Does anyone else have any other questions? Welcome to ask them here or write them in the chat.
Hi, can you hear me?
Yes, very well.
Okay, thank you very much. Nice talk. I have a follow-up question for the multi-site harmonization.
Okay.
So, so what kind of training data sets do we need to have to do this multi-site harmonization? For example, if we have like 2 sites, do we need to have like the same subjects scanned on 2 different sites, or can be different subjects?
Yes. That's a very good question. You know what? We did both. we have two data sets. One data set is one person who traveled all across the country and got his brain scanned into, I think, 30 different hospitals. So that's the data set.
So one person?
And we get some very interesting results. But we have also a data set that whose images were acquired for I think more than 400 different patients in I think 20 different hospitals. And we implemented, I don't want to get too much in the details, but what we call an adversarial system, where on the one hand side we encode the image into a new harmonized image. And on the other side, so that's one neural network, and there's another neural network that is called the discriminator that tries to recover, where does that image got acquired from. And in both cases, we got very good results. So there's no clear cut. It's not like first set of data, it's not going to work. Second set of data, it's going to work. The only thing that I'm more or less sure about is if we harmonize on 20 or 30 different hospitals, how good is it going to be on images acquired on yet even more hospitals? This is still unclear. We haven't did that experiment so far. I'm expecting that we will be doing this probably in 2021 or so. So in 1 year from now, I should have an answer for that.
Okay, thank you. But for multiple sites, do you choose one site as a reference and harmonizing all the other sites to these?
No. The way, at least our implementation, the way it works, we have a neural network that takes as input an image and output a new image, and the goal is that this new image needs to be it needs to be completely agnostic from where it got acquired. So it's not like a registration process where we try to make all of the images of every hospital look like the hospital one. It's like more, we take all of the images that came from all of the hospitals to look like none of those images, but at the same time, it's still a brain image or MRI brain, image that you can work with.
Okay, very interesting. So do you have like any papers on these two projects? I can look into.
Not yet.
Okay, I'll keep
towards the end of the summer, we should be working on the paper. But if you want, you can drop me an email. I can give you one or two references of some things we have done in the past that I would say are very similar to that.
Okay, thank you very much.
Now. Yeah.
Yep.
Okay, we have another question in the chat. Do you perform augmentation after harmonization? If not, would the model be thrown off if the input image was translated 50 pixels to the right, for example?
ConvNets are robust to translation, so that's not an issue. But do we do the augmentation? We always do augmentation. Irregardless, each time you train a neural network, you always do data augmentation. So I've not talked about data augmentation in the presentation, but each time we do this. And ironically, we have a paper at middle this year where we show how we can synthetically generate images and how data augmentation even further improve results. So the answer is yes, totally.
Okay, great. Did that answer your question? If you have any more questions, please write them in the chat or ask right here. All right, it did answer
Good, thank you.
your question.